UMAP takes data with many measurements per item and draws it in 2 dimensions. Its central strategy has 2 stages. First, it converts the original data into a weighted neighbor graph. Second, it moves low-dimensional points until their graph resembles the original graph. The graph is the bridge between data and picture. Algorithm 1 names 5 inputs. X is the original set of data points. N is the number of neighbors used to describe each local area. D is the desired output dimension, usually 2. Minimum distance and the number of epochs control the final layout and how much optimization work is performed. For every point X, UMAP finds its N nearest neighbors and records their distances. This produces 1 local view per point. Importantly, UMAP does not assume that one global distance scale describes every region equally well. A dense region and a sparse region can use different local normalizations. Each neighborhood receives 2 useful numbers. Rho is based on the nearest neighbor distance and acts like a local offset. Sigma controls how quickly connection strength falls as distance grows. Algorithm 3 uses binary search to choose sigma, so the effective neighborhood size matches the chosen number of neighbors. Now distance becomes an edge strength between 0 and 1. A very close neighbor receives a weight near 1. A farther neighbor receives a smaller weight through exponential decay. These are graded relationships, not hard cluster assignments. The graph can express that one neighbor is much more convincing than another. Local relationships can be asymmetric. Point I may regard point J as very close, even when J has a different local scale. UMAP combines the 2 directed strengths with a probabilistic union. Add both strengths, then subtract their product. This produces 1 undirected edge while preserving evidence from either local view. After these local graphs are merged, the original coordinates are no longer the main object being optimized. UMAP works with nodes and weighted edges. The low-dimensional map receives new coordinates, but its purpose is to recreate a similar pattern of strong and weak connections. Exact original distances are not directly copied. Before gradient updates begin, the paper uses spectral embedding for initialization. It builds a weighted adjacency matrix, computes a normalized graph Laplacian, and takes selected eigenvectors as starting coordinates. In plain language, the global connectivity pattern supplies a structured first draft of the map instead of a completely arbitrary arrangement. The objective compares edge membership in 2 spaces. Mu is the strength of an edge in the source graph. Nu is the strength implied by the current low-dimensional positions. Fuzzy set cross-entropy penalizes strong source edges that disappear and strong map edges that should not exist. The loss compares graph relationships, not every raw distance. Algorithm 5 reduces that loss with stochastic gradient descent. Strong source edges are sampled and their endpoints attract. Randomly sampled non-edges act as negative examples and create repulsion. This negative sampling avoids processing every possible pair of points. Repeated updates reshape the map while the learning rate gradually decreases. Here is a derived 4-point example, verified by a deterministic script. A and B are each other's nearest neighbors. C and D are each other's nearest neighbors. The local graph, therefore, contains 2 strong pairs and a much weaker connection across them. A 2-dimensional optimizer should keep each pair close without claiming an exact distance between the pairs. Read a UMAP plot as a map of neighborhoods, not a ruler. Closed local relationships are the main signal. The distance between far clusters, the empty space around them, and even apparent cluster size can change with settings and random seed. UMAP is useful for exploring structure, but the picture alone does not prove global geometry.